Yeah, so let's start. So today we'll first solve last year's week 9 assignment. Then we'll solve this year's week 9 practice assignment and then this year's week 8 assignment. Okay. So the first problem is, suppose we are able to show that BPP equals P, then which of the following will be true? Select all that is or are correct. There exists a BPP complete problem. P equals NP. Polynomial identity testing is in P and P equals sigma 2P. So which of these four are correct?
So, as such, we do not have BPP complete problems.
Right.
So, what could be the meaning of solving this BPP into P? That all the strings which are the part of the languages can be decided in
Okay, so BPP equals P just means that every language in BPP is also in P, right?
every language in.
PPP is also in P.
Yes.
Yeah. Okay, so yeah, so the answers are A and C, and let's see why. So if BPP, okay, let me write it. So uh, s- if BPP equals P, then since every language in P except the empty language and the universal language, P complete, uh, every language will be BPP. Yeah. So every language in P except these two are P complete. So can you tell me why?
So, I mean, uh, except phi, everything can be whichever problem is solvable in the polynomial time.
Right.
Uh, I mean, can be reduced to another PP problem, right?
Right. Okay. So and what would that reduction be? So suppose you have two problems in P, A and B, and you want to reduce A to B. So what would a reduction look like?
So a reduction will look like, say, if x is an instance of L1, then the
Right.
f of x would be the element of L2. But
Okay. Right.
then
But
such a
yeah.
reduction cannot be straightforward. Like, say, if minimum spanning tree is reducible in the polynomial time, and say getting the say the Euler's path is also solvable in the polynomial time. So then, how would I reduce an instance of the MST into an instance of the Euler's path then?
Okay. So my claim is for languages in P, there is a very trivial reduction.
For what did you say? Can you please say again?
Yeah. So what I'm saying is for languages in P,
Hmm.
there is a very trivial reduction. So if A and B are both in P and neither of them is one of these two, then there is a very trivial F mapping A to B.
Uh, yes, but then I mean, how can we carry out such a mapping? Like the example which I gave you. So, what could be the mapping that maps an instance of the MST to an instance of the Euler's path?
Okay, it's very simple. It's this. Take an instance of MSP,
Yes.
solve it.
Mm-hmm.
If it is a yes instance, map it to any arbitrary yes instance of Euler's path problem. And if it's a no instance, map it to any no instance of Euler's path problem. So all you have to do is fix two instances. Let's call them x1 and x2 of Euler's path problem. One is a yes instance, another is a no instance. That's it.
Yes.
And this works because since the first problem is in P, you can actually solve it in
Yes.
polynomial time, right? So the reduction is very trivial. It, Agreed. Unlike reductions in NP, this doesn't tell you much about how the two problems are related, but it is still a reduction, right? A polynomial time reduction.
Yes.
Yeah.
And what about this cleaning closure of this 0 comma 1? So which encompasses everything then?
Okay, so why can't these two be complete? Because okay, what did I say in the reduction? You need to fix x1 and x2. One of them is a yes instance, another is a no instance, right?
Yes.
But if the language is pi, then there are no yes instances. If the language is 0, comma 1 star, there are no instances, right?
Yes. Yes. Yeah,
So
I got it.
so if your language were 0, comma 1 star, how would you map a no instance of the MST problem to some no instance of 0, comma 1 star, right?
Yes.
Yeah, so every language in P except these two are P complete.
Right.
Okay, and so if BPP were equals to P, every language in BPP except these two would be BPP complete, right?
Yes.
Yeah, so that is why A is true. And what about C? Yeah, so we know this, right? Polynomial identity testing is in CoRP. Yeah, and CoRP is contained in BPP equals P. Yeah,
Mhm.
so C is also true.
Yes.
Yeah, and we can't say anything about A and D because like P and BPP, like we don't know anything about P versus NP and P versus sigma 2P, right?
Hmm.
Yeah,
So if we go as per the definition of BPP and P,
right.
then what could be the, I mean, what could be the intuition behind the meaning of the equality of the BPP and P?
Okay, so P and BPP are sets, right?
Yes.
And they are sets of languages. And we already know that P is contained in BPP, right?
P is contained in BPP, yeah, it's true. But then if we go as per the definition that BPP is accepting all the strings with all the valid strings with the probability of say 2 by third.
Okay, but oh
And
no, that is not what BPP is, right? That is what a language in BPP is, right?
yes.
So what is the definition of BPP? It's a class of all languages L accepted by randomized Turing machines, such that
Mhm.
if X is in L, the acceptance probability is at least two-thirds. If X is not in L, then the rejection probability is at least two-thirds, right?
Yes.
Yeah, so if suppose something were in P, then you have a deterministic Turing machine for it, right?
Right.
And every deterministic Turing machine is also a randomized Turing machine, right? Because it does throw random coins, it just completely ignores them.
Yes.
So when X is in L, for every random coin it accepts, and for when X is not in L, for every random coin it rejects, right?
Yes.
And if it since it does it for every set of random coins in both cases, it also does it for at least two-thirds many random coins, right?
Yes. Yes. Yeah.
Yeah, so P is in BPP.
Yes. Right. Yeah.
And what
I'm.
about PPP, BPP equals P? Well, they are sets, so they would be equal if both are contained in each other.
Mhm.
So we
So
already know this. P is contained in BPP. If we also knew this, then they would be equal.
yes.
Yeah.
But then can this ever happen that a probabilistic Turing machine may become equal to the deterministic Turing machine?
Okay. Yeah. So that's a good question. A probabilistic Turing machine may not be equal to a deterministic Turing machine, but but what you can what can happen is the following, right? For every probabilistic Turing machine, there exists a deterministic Turing machine which accepts the same language. So you are not so the two Turing machines might not be the same, but they might still accept the same language, right?
Yes,
In
yes.
fact, you also face this problem with the P versus NP problem, right? Because for a language in NP, you have a non-deterministic Turing machine, right?
Yes.
And okay, and P would be equal to NP. That means that for every language in NP, there exists a deterministic Turing machine accepting it. The non-deterministic Turing machine and the deterministic Turing machine need not be the same. They must just exist, right?
Yes.
Yeah, yeah. And in fact, we expect BPP to be equal to P.
Mhm.
Yeah. So is this fine?
Yes, yes.
Yeah. Okay, so then let's look at the next problem. So given a Boolean formula phi equals x1 or not x2 and x1 or x2 and x1 complement or x3, the number of satisfying assignments of phi is what? Okay, so I won't ask you what this is because this needs to be worked out. But okay, so one way to do it is just like try all the eight possible assignments and see which satisfy the formula. Another way is to try to simplify the formula. Okay, so the formula over here is okay. So can you tell me what I can write these two as? Okay,
Two,
so
which,
yeah, so what I'm saying is I can simplify this expression into a simpler one. So can you tell me what the simpler expression equivalent to this is?
okay.
Yeah, you are right. It's x1. Yeah, so my claim is this is just equals to x1 and x1 complement. Wait. There should be an or over here, not an and. Yeah. So do you see why this is equivalent to x1?
So this might be a known result, I don't know. But seems that it is yeah, it's because because to make everything true,
Hmm.
uh, so if I put the value of x1 as true, so then x2 could be anything. It could be true, it could be false. So the value of x2 doesn't matter actually here. So
Okay.
what matters here is the value of x1 only. So probably maybe
Okay.
because of this, this entire thing can be reduced to x1.
Yeah. Another way of seeing it is like this, that this is x1 or x2 and x1 or sorry, x1 or x2 complement and x1 or x2, right?
Yes, yes, that is also true. Yeah.
Yeah. So like so from this you can take x1 common.
Yes,
Yeah.
yes,
And
that
then
that
you
is.
get yeah. So then you would get x1 or x2, x1 and x2 or x2 complement. But x2 or x2 complement is 1.
Yes, yes,
Yeah.
yes.
So we get this. And now it's easy to find out the number of satisfying assignments, right? So x1 equals 1 forces uh, x3 uh, equals 1, right?
Even this expression can also be simplified as x1 or x3 only, isn't it?
Wait.
Because if we go for distribution, then it will become x1 and the complement of x1, which would be a contradiction. Or so basically a false value always, and then or the x1 union and x3. So the false won't matter. So this will result into a simple value x1 or x3. So now we can verify that which all values will result into the true value here. So we can have two values of x1 and x2. So yeah, and
No, so
so out
this
of
is
both
not
of the
equivalent
following,
to x1 or x3, right? Because x1 or x3 is true when x1 is
final answer would
0.
be 3 then.
Yeah, so this is not equivalent to x1 or x3 because if x1 were
Your
0,
your video got freezed actually. Yeah,
okay,
so
okay,
could
yeah.
not hear. I mean, it was frozen for some time.
Okay, yeah. So this thing is not equivalent to x1 or x3. This is equivalent to x1 and x3. So if you want to do it, it's like this. So this is equal to x1 and x1 complement or x1 and x3.
Yes, yes, yes. Yeah, right,
Yeah.
right.
So this is x1 and x3.
Correct.
And so both x1 equals to x3 equals to 1, right?
So single assignment. Yeah.
Uh, Actually, two assignments.
X2 is equal to 0, comma 1. Why so?
Okay, so this formula is okay. This formula is equivalent to x1 and x3, right? And
Yes,
so like this is satisfied whenever this is satisfied, right?
yes,
And this is satisfied when x1 and x3 are 1 and x2 is anything. Since x2 doesn't even appear over here, it doesn't matter, right? What value
yes,
I give to it.
yes, yes, yes. Right,
So
right.
then this should also be satisfied for both values, right?
Yes,
And you can directly check that this is satisfied because whenever I put this to be 1, it doesn't matter what x2 is. Both of these are 1. And whenever this is 1, this is also 1.
yes, yes.
Yeah. So there are two satisfying assignments, 101 and 110.
Yeah.
Yeah. So is this fine?
Yes, yes.
Yeah. Okay, so the next problem is which of the following is or are yes instances of the unique set problem? Consider all the below formulas as over three variables x1, x2, x3. And this part is important. Okay.
Yeah. So, but then how to how to know that whether for each of the problem here we have got exactly one assignment?
Yeah, so one way is to like try all the eight assignments. Another way is to simplify and see how many do something similar to this. Simplify and then check how many assignments do you get.
Okay.
Yeah, but even before that, what is the unique set problem?
So unique set is like the promise problem wherein we should have exactly one satisfying assignment, and otherwise, it would say yes if there exists only one satisfying assignment. Otherwise, it will say zero.
Okay, yeah. So, okay, okay. One way to think about unique set is this. Yeah, so a formula phi is in unique set, or a formula phi is a yes instance of unique set if it is satisfiable and has exactly one satisfying assignment, and it is a no instance of unique set if it is unsatisfiable. Okay.
Yes,
And what about a formula which is satisfiable but has more than one satisfying assignments? We don't care about such formulas,
yes, yes,
right? Yeah, so let's look at all four options. So A is x1 or x2 complement and x1 or x2 and x1 or x3, right? So again, just as in the previous question, we can simplify this, right?
yes. This will become x1 then.
Yeah, so it's x1 and x1 or x3. Now we can
So
either further simplify this or just say that x1 equals 1. Okay, we don't need anything from this. Just this is sufficient to show that this is not a yes instance. Yeah, so can you tell me why? You can immediately say this is not a yes instance.
uh, no, no, no. I put the value of x1 as true. So then this entire thing will result into a true value.
Yeah. But we are looking at unique set, not set.
So this has got only, yeah. So in this case, yeah. So
Yeah,
yes, x2 could be anything. Yeah,
yeah.
right.
So yeah, x2 can be 0 or 1.
Uh-huh.
So yeah, since one variable doesn't even appear in the formula, it cannot be part of unique set, right?
Yes.
Yeah, so A is not a yes instance. What about B? X1 or x2 complement. So again, we can directly say that this is not a yes instance. Why?
Uh, this is x1 and this thing. So x1 and the complement of it, which is contradiction, and
Okay.
x1 and x2.
So okay, why is this a contradiction? This is x1 and x1 complement or x2. So x1 is 1 and yeah, so this has a satisfying assignment. X1 equals 1, x2 equals 1.
Yes.
Again, we are supposed to be considering these as formulas over three variables.
So because third variable is not here.
Right, yeah. So it can take any value, right? 0 or 1. So there are two possibilities. Either this formula is false, in which case this is directly not. So in this case, this is a no instance of unique set, right?
Yes.
Uh, another case is this formula is satisfiable, but in that case, X3 can take any assignment and that would still give you a satisfying assignment, right?
But then I can include x3 as a dummy variable here, even
Uh,
though x3 is not here.
so your voice broke. Can you please repeat?
Yeah. So I can take x3 as a dummy variable here,
Right. So,
just
okay.
to.
So one way to include it would be this, no, and sorry, and x3 or x3 complement.
Yes.
Yeah.
Uh,
So yeah. So yeah, that was my point. X3 can be assigned 0 or 1. Yeah. So the thing is, like, there are only two possibilities. Either this is a no instance, in which case we are done. If this is satisfiable, then since we are considering this as a formula over three variables, take any satisfying assignment that assigns values to x1 and x2 and put x3 equals to 0 and x3 equals 1. Both would be satisfying assignments. So if this is satisfiable, then this would have at least two satisfying assignments, right?
yes.
And so this can never be a yes instance. So in both cases, let me just write this down. Not a yes instance because, yeah. So now let's look at C. What is C?
C is definitely a yes instance.
Yeah. Okay. Let me first try to tell you why.
Because after this or the second term is false. So therefore the first term has to be
Yes.
has to return it true, and then we can have only one assignment because in the first term we have only ends and do not have
Right.
ors.
So the only satisfying assignment is x1 equals x2 equals 1, x3 equals 0. So this is the yes instance. And finally the x1 and x2. Okay, so yeah, I'm not sure if it would be easy to simplify this. Yeah. Yeah, so I don't see a direct way to simplify this. So let's just try some assignments. So x1 equals to 1 forces x3 to be 1 as well, right? Oh, no, 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 yeah, okay, this is much simpler, yeah. Okay, so x1 equals to x2 equals to 1 is a satisfying assignment,
Yes.
right? Okay, or rather, let me write it like this. X1 equals to x2 equals to 1 is enough to satisfy the formula. So there are at least two satisfying assignments. Yeah. So this is also not a yes instance. So the only yes instance is C.
Yes.
Yeah.
So I have a query here that if I
Yeah.
consider the promise variant of a problem, then
Right.
which one would be tougher, the promise variant of a problem or the problem in origin? And the original problem.
Okay. So by tougher, what do you mean?
So yeah, so like say if the original problem is says NP complete,
Okay.
then what can we say about the promised version of the problem P? Will it be NP complete or
Okay. So first of all, the promise prob. Okay. So it doesn't make sense to say that the promise problem is NP complete, right? Because NP is a class of languages.
yes?
So, okay, what you can still ask is the promise version NP hard? In the sense that if you can solve it in polynomial time, you can solve all NP complete problems in polynomial time. That is still a valid question, right?
No, 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 I did not understand this. What
Okay,
did you say?
so okay, so what I'm saying is the following question is still a valid question. If a problem is NP complete, is its promise version NP hard? In the sense that if I can solve the promise version in polynomial time, I can also solve the NP-complete problem in polynomial time.
Ha. So and why so? Because if I
No,
can
no,
solve
no,
the
no, okay, okay. This is I'm not making this claim. What I'm saying is, what would it mean to say that the promise problem is NP hard?
and why not the promised version is NP complete?
Okay, so it can't be NP complete because it can't be in NP, right? Because NP is a class of languages,
Yes.
and like promise problems are a generalization of languages, right?
Yes.
Yeah, so a promise problem can definitely not be in NP. So all you can ask is, okay, if I can solve it in polynomial time, can I solve all problems in NP in polynomial time as well, right? That is still a valid question.
But still, it is difficult for me to digest that why the promised version cannot be an element of NP, wherein we are saying that okay, so yes, I mean we do have yes instance, we do have no instances.
Right, but we also have don't care, right? So, okay, what's the difference between a language and a promise problem? Take any x, any string x, there are only two possibilities for a language, right? It is either in the language, so it is a yes instance, or it is not in the language, that is, it's a no instance, right?
I got it. Yeah. So
Yeah,
it would be yeah. So it would be meaningful to make the statement that if the can the promised version of the problem be NP hard?
right. That still makes sense, but again, there is an issue. You have to define the reduction correctly over here. So, okay, what was the reduction between two languages? X is in language one, if and only if f of x is in language two, right?
Yes.
But now, for promise problems, there are three things. Yes instances, no instances, and don't care, right? So, one way to define a reduction is this. Let's say you have a language L and a promise problem A. L reduces to A if x is in L implies f of x is a yes instance of A, and x is not in L implies f of x is a no instance of A.
So I can define it like this also. Say f of x is a yes instance or it is don't care condition. Don't care
Okay,
can be included in both the sides, like similar to the BPP kind of thing,
right,
right?
but
So, yeah.
yeah, then there is one issue, right? So suppose I could solve problem A in polynomial time. Okay,
Yes.
I still can't solve L in polynomial time. Why? Because when I say don't care, okay, so okay, when something is in don't care, what will your algorithm say? It can either say one, it can either say zero, right? So just
Yes.
because your algorithm outputs one does not mean that you have a yes instance, right? So just because you took x, computed f of x, and fed f of x to your algorithm said f1, you can't conclude that x is in L, right?
Yes.
Yeah, so I mean, this is still a valid reduction, but over here, so as I said a few classes back, when we are defining reductions, we should have some problem in mind, right?
Yes.
So over here, what complexity theory question do we have in mind? Uh, is the promise version of an NP-complete problem NP-hard? That is, if I can solve the promise version in polynomial time, can I also can I say that NP equals P? This is the question we have in mind, right?
Yes. Yes.
And for this question, which reduction makes more sense? The one I said, right?
Yes.
Because in that case, if every yes instance of L map to a yes instance of A, and every no instance of L map to no instance of A, just by feeding f of x to an algorithm for A, and you let's say if it outputted 1, you know x is a yes instance of L. If it outputted 0, you know x is a no instance of L, right?
Yes. Yes.
Yeah, so this reduction makes more sense, mapping yes to yes, no to no.
Right. Right. Right.
Yeah. Yeah, so coming to your original question, are promised versions of NP complete problems NP hard? Again, there is one more issue. How do you define? So it depends on how you define the promised version, right? So, for example, take 3SAT.
Yes.
How do you want to define the promised version of 3SAT?
So, so I have yes instance, I have no instance, and then and for the don't care conditions, so don't care conditions can be uh, yeah, difficult to don't
Empty.
care condition. Yeah.
So there are three sets, right? Yes instances, no instances, don't care, right? Make
Yes.
don't care empty.
Yes.
So basically, every language is also a promise problem, right?
Yes.
So what you can say is 3SAT is a language. The corresponding promise problem is exactly the same.
Mhm.
Yes, since these are satisfiable formulas, those since these are not satisfiable formulas, there is no don't care over here.
Yes.
And now what you're asking is this NP hard, right?
Yes.
Well, it still is, right?
Could not hear you. Yeah.
So it still is NP hard, right? Because yeah, the promise version is exactly the language. If you define it like this, right?
Yes. So will it be equally hard as the other problems in
Yeah.
NP? The problem
Yes,
itself is
okay.
not the element of NP. It's true, but then will it be equally hard, or at least as hard as the other problems in NPR?
Yes, so if we define the promise problem like this, take the language, make it the promise problem, then yes.
Okay.
Yeah. So now we can also say that this is in NP because sure, it's a promise problem, but it is a language.
Yes.
So the
Yes.
crucial thing is how are you going to define the promise problem?
Mhm, mhm.
Yeah. For example, you can also consider a unique set, a promise version of that, right?
Yes. Yes.
Yeah. So that promise okay, so you have to define what that promise is to define a promise version. Because in case of unique set, the promise is you are not going to get instances which are satisfiable but have two or more assignments, right?
Yes.
That's the promise over here.
Yes. Yes.
Yeah. So
Yes.
yeah,
Understandable. Yeah.
yeah.
Can clear to me. Yeah.
But that said, there is something called so we have promised BPP, right?
Mhm,
Similarly, we have promised NP as well,
mhm,
and you can like ask similar questions about it. For example, is three set promise NP complete?
mhm.
Yeah. So I won't define what promise NP is, but yeah, these type of questions still make sense.
Okay. Okay. Okay.
Yeah. Okay. So let's look at the next problem. The next problem is let G equals A union B, comma E be a bipetite graph where size of A and size of B is N. If G has no perfect matrix, then which of the following statements is true about the adjacency matrix of G? Both the determinant and permanent are zero. Determinant is zero, but the permanent may not be zero. Permanent is zero, but the determinant may not be zero, and neither the determinant nor the permanent may be zero. So which of this is true?
Even though in the previous discussion you
Yeah.
explained this permanent term and it is explained in this lecture video also, but
Okay.
this permanent term is not clear. So can you quickly elaborate what this permanent refers to? That formula, that sigma term, and then sigma
Okay.
ij,
Okay.
and then
Yeah.
you
Yeah.
wrote something like that.
Okay. So A and B are already used over here. So let M be a matrix. And permanent of M, sum over all permutations on N, product over all I in N, Mi sigma I. So this is the permanent of N.
How to interpret this? Still, this seems very complicated. So, I mean, in layman terms, what could be the meaning of this permanent?
Okay, so okay, in layman terms, one way to look at it is it's a polynomial. So
Mhm.
because what I could have done is I could have defined it something like this, right? So instead of saying that M is an n cross n matrix made up of numbers, I could have M is an n cross n matrix whose entries are variables, right?
Actually, your voice is not that
Okay,
clear. Probably you are. Yeah. So if you speak bit slow, then probably because there is some issue in the network. Could be an issue. I don't
okay,
know from my side also. But if you better if you write down the things which are important one or important assumptions, then yeah, that would be easy to understand.
okay. So yeah, so this is the permanent, and what I was saying is one interpretation of the permanent is as follows: let M be an n cross n matrix whose entries are variables. Okay, Can you hear me?
Encrosen matrix where
Where all of these are its entries are variables, not numbers,
okay, and yeah, fine, entries are variables, yeah.
right? So then this is just a polynomial, right?
Hmm.
Yeah, so that is one interpretation of the permanent.
Okay.
Yeah.
So
Another
what this
inter yeah,
like say so what could be the meaning of M one comma say three,
okay,
say
so
the first row and third column?
right, so it's the entry in the first one, third column.
So can you take a small example, say a
Yeah,
small
yeah, yeah. I was
and then
planning on doing that. That would be easier. So let M be 1, 2, 3, 4. Okay, so then permanent of M is sum overall sigma in S2 product over I in 2 Mi sigma. Okay, so now how many permutations are there on just two elements?
so factorial two elements.
Right, so there are just two permutations, right? One
Yes.
maps to one, two maps to two, and two maps to one maps to two, right?
Yes.
Yeah, so let me, so it's uh, M 1 comma 1, M 2 comma 2 plus M 2 comma 1, M 1, okay, no, no, M 1 comma 2, M 2 comma 1, right?
Hmm. Hmm.
Yeah, because, okay, so over here, the permutation maps 1 to 1 and 2 to 2. Okay, so this is
Yes.
the permutation I considered, and then product I into Mi sigma I is just M1 sigma 1, which is 1, M2 sigma 2, which is 2, right?
Yes.
Similarly, over here, the permutation maps 1 to 2 and 2 to 1.
Yes. Yes.
So over here, M1 sigma 1 is M1 comma 2 and M2 sigma 2 is M2 comma 1, right?
Yeah. Yeah.
And what is this? This is 1 times 4 plus 2 times 3, which is 10, right?
Yes.
Yeah, so this is the permanent of this matrix.
Yes.
Yeah.
And how this idea of permanent is related to the perfect bipartite matching then?
So that we argued in last class, right? That the number of perfect matchings in a bipartite graph is equal to the permanent of the adjacency matrix.
Okay.
Yeah.
Okay.
So do you want me to prove that again, or should I just like use that claim?
No, no, since this permanent matrix is now clear to me, so yeah, I would be able to
Yeah.
understand this stuff by seeing the previous session's video then.
Yeah. Okay. So yeah. So okay. To solve this problem, let me first write this claim that we proved last time. Uh, yeah. So this we proved last time, right?
Yes, yes.
Yeah. So okay. Now using just this claim, can you rule out some of the options?
Can you please scroll down a bit wherein the claim is written?
Yeah.
Yeah.
This. Yeah. And these are the options. and our graph has no perfect matchings.
Hmm. So, since no perfect matching is there, so I can at least say that this permanent value is zero.
Right. So
So,
it rules out D, right? And P and D are ruled out. So this and these are ruled out, right?
yes.
Yeah. So now, okay. So now we have to decide what the determinant is. Okay. So the main idea of this question is the following. Last time we saw connection between the permanent and perfect matchings. Using that, you can solve half of the question. To solve this question completely, you also need to know a connection between the determinant and perfect matchings, right?
Yes.
Yeah, so that's what I'm going to do now. Yeah, how should I write it? Yeah, yeah. So this is the claim. So I'm claiming that if the determinant is non-zero, then G must have a perfect maximum. Okay, and the proof. Okay, so first of all, yeah. So first of all, was this characterization of determinant covered in class?
So like in this calculation, if instead of plus, if we put a minus, then this will become the value of the determinant, the value which we computed just now.
So where do we put minus in place of plus?
M11 and then M12 minus this thing,
Right.
M22
Yes.
minus this.
Yes. Yeah. Yeah. So that is
So
true. What I'm asking is this characterization of determinant was this covered in class? Like, was this mentioned in class?
it was not covered in the class.
Okay. Yeah. So then I should tell you what this sine sigma is, right? Okay. So my
Yeah.
claim is determinant is equal to this quantity. Ignore this for now. So okay. So what? Okay. I'm not going to prove that this is what the determinant looks like, but let's first ignore this and let me give you some intuitive idea of why this is true. So as you said, over here, if you replace the plus by minus, you get a determinant, right?
Yes.
Now, okay, so do you recall how we would compute the determinant? Let's say you have an n cross n matrix. One way to compute the determinant is like hide the first row, hide the first column, compute the determinant of the remaining matrix, multiply it by the first one comma one entry, right?
Yes.
Do this for then like hide the first row, second column, and so on, right?
Hmm.
So if you see over here, this permutation is still coming in, right? Why? Because I hit the first row, first column. That means that I mapped the first row to the first column. Okay.
Hmm.
And then let's say the determinant of the remaining matrix has this structure. Then what would the complete permutation look like? It would map 1 to 1. And for 2 to n, it would map whatever the smaller permutation maps it to. So basically what I'm saying is this. If you were to sit down with that formula of that way of computing the determinant
Hmm.
and like completely expand it out, term by term,
Hmm.
then you would get exactly this. So that's a way to prove this. That's one way to prove this.
Okay.
Yeah. But but I still haven't told you what sine of sigma is. Okay.
Hmm.
So Sigma is a
Sigma is a
permutation.
permutation
Yeah.
of the signs, so different possibilities, plus two minus or minus two plus kind of a thing or what?
Okay, no, no. So sigma is a permutation, right? Now it turns out you can write every permutation. So, okay, you can think of a permutation as this. Start with an array 1 to n, okay? And your end goal is to obtain the array sigma 1, sigma 2 up to sigma n, okay? What you can do is you can just flip two elements at a time. If the number of flips required is odd, then the sign is -1. If the number of flips required is even, the sign is 1. Sorry, yeah, the sign is +1. Okay, so, okay, let me write this. Move this to the next page and write this. Yeah, okay, so these are the two arrays. Now, first of all, notice that because sigma is a permutation, this array also contains 1 to n exactly once. Is that clear?
Yes,
Yeah. So basically, both of these arrays contain the same elements but in different order.
right.
So what I can do is I can by changing the order of elements in this array, I can move to this array, right?
Yes.
Yeah. And here's how we are going to do it. So we want to obtain. Yeah, so this is how we want to move from A to B. We are just going to swap two elements at a time.
Okay. So two elements, like say the one and two will get swapped, and then
No, no,
three
no.
and four.
Any two elements.
Okay.
So
Okay. Perfect.
yeah, so
Perfect.
okay, so basically think of it as a game. You have one array, you have another array, and the rules of the game only allow you to swap two elements at a time. Any two
Okay.
elements.
Okay.
Yeah, so for example, I could have swapped 1 and 10. So then the array would look like 10 to 3 up to 9, 1, 11, and so on, right?
Ah. Okay. Okay. So only
Yeah,
two elements are going to be swapped, or exactly two elements are going to be swapped.
I mean, you can't swap one element, right? So okay, so what you're allowed to do is the following. This is an iterative process. In each iteration, you can swap exactly two elements.
Okay. Okay.
So for example, if I were to swap 1 and 10, my array would look like 10, comma 2, comma 3, comma up to 9, comma 1, comma 11, 12, and so on.
Mhm.
Okay. And by doing this repeatedly, you want to get sigma 1 to sigma n.
Mhm.
Is the process clear?
Uh, yes, so how do I view this sigma 1 to sigma n is that this is just a permutation of the
Right.
elements 1 to n, that's it.
Yes.
And yeah, that's nothing more than, I mean, so I do not find any significance of this two element theory here, because if I've been given say five number of the elements, I can find its permutation, and I call that permutation as say, sigma 1 to sigma n.
Yeah. So okay. So whenever I'm swapping two elements, this is a
Mhm.
very special type of permutation, right?
Okay.
In fact, this is sort of the smallest non-trivial. This is the smallest type of non-trivial permutation, right?
So like say, can you write here one, two, three, four, five? Just I mean
Okay, yeah,
an array having 5 elements only.
yes,
Uh, and to understand this swapping of the two elements, say if I swap one and three, so this will look like say what
okay,
three, two, one, four, five,
yes, 3, 2, 1,
one, four,
4,
five.
5.
And in the next iteration, if I swap the first and the last element, so it will look like say 5, 2, 1, 4, 3.
5, 2, 1, 4, 3. Yes.
So what is special with this permutation?
Okay, right.
Yeah,
So two things. One is this is the this is the smallest type of non-trivial permutation, right? Because this is a trivial permutation.
I got it. Yeah. So
Yeah,
yeah, non-trivial. Fine.
yeah. So this is one thing. Another thing is what I'm going to write. So okay, for now, accept that we are doing this. So yeah, we want to obtain B from A by swapping two elements at a time. If we need an odd number of swaps, sin of sigma is negative, and if we need an even number of swaps, then sin of sigma or SGN or SIGN. Yeah, so this is how the sign is defined. Okay.
Yes. And why do we? I mean, for what purpose do we require even or the odd number of the swaps? We just want a different permutation. So
Right. So yeah, so you want to get A from B using the smallest non-trivial operation, right?
yes,
And what
yes,
I'm saying is just this. If the number of swaps required is odd, the sign is -1. If the number of swaps required is even, the sign is +1. Okay. So is the definition clear? Because I'm going to say something more about it. But is the definition clear? Okay. The purpose behind the definition might not be
yes,
clear, but
yes,
is the
clear,
definition
clear.
just clear? Right. Okay.
Yes,
So
clear.
you should have, you might have noticed one curious thing about definition. I'm saying if we need an odd number of swaps, sign is -1. If I need an even number of swaps, sign is +1. But what if one way of going from A to B requires an odd number of swaps, another way requires an even number of swaps? That
Uh,
might be possible, right?
yes, might be possible. Might be possible. So does this mean that we can have different splits, no doubt in this, but then both the different splits should either contain the even number of the swaps or the odd number of the swaps.
Yeah, that is true. So for every permutation, it turns out that the following is true. That you can go from one to n to sigma 1 to sigma n in multiple ways. And like by just swapping two elements. And let's say one way of going requires k swaps, and another way of going requires l swaps. K and l need not be same; they can be different. But either both of them are going to be odd or both of them are going to be even.
Yes, yes, yes.
This you can prove. The proof is not simple, but this is known.
This is a known result, I think, because
Yeah,
I could immediately recall this result. So that is what I
yeah,
took.
yeah. So this is another thing that is special about like swaps,
Yes,
just swapping two elements at a time.
yes, yes,
Yeah. Yeah, so this was the definition of sign, and this is the definition of determinant. Okay. But
yes,
other, okay, so you can also define the determinant like this. But the way you like one way to see this is the following. Start off with the usual definition of the determinant that you already know. Remove the first row, remove the first column, compute the determinant, the remaining matrix, do the same for the first row, second column, and so on. Right.
yes.
Try it if you want. You can try this. Starting with that definition, you will be able to arrive at this definition.
Okay.
Yeah,
Okay.
yeah. So I won't prove it, but yeah, this is it's possible to prove. So this is the determinant, and now what did we want to prove? We wanted to prove this.
Mhm.
Yeah. So let me now prove this. The proof is just one line.
So
So
sometimes you write PM and sometimes you write PMS. So what's the difference? I mean, how do
wait,
you?
PMS.
Yes.
Oh, okay, okay. PMS is perfect matching. PM is
And
perfect matching, singular.
okay, okay, all right. Yeah,
Yeah, I mean, okay, yeah. I mean, I should write the entire thing, but yeah, I don't want to write the entire thing over and over again.
yeah,
So PM stands for perfect matching. S
yeah,
means plural. Yeah.
yes.
So if the determinant is non-zero, then G has a perfect matching. Okay, so if the determinant is non-zero, there exists a sigma in Sn such that product I in N mi comma sigma I is not equals to zero. So this is my claim. Does this claim make sense?
Uh, yes. So if determinant is not zero, then yeah. So the product of these things, and we do not use summation here.
No, no, no. I did not use that. That's actually the claim. So suppose this quantity, okay, suppose this quantity is non-zero, okay. What I'm saying is, for at least some sigma, this quantity must be non-zero.
Yes, yes, right, right.
Why? Because if, okay, so this quantity is the same as this quantity, right?
Hmm.
So suppose for every sigma, this quantity were zero.
Hmm.
Then what would be this? This would be a sum of plus or minus zeros, right?
Yes, yes,
And that
yes,
cannot be non-zero.
yes,
Yeah, so the moment I say this entire thing is non-zero, at least one of these products must be non-zero, right?
yes.
Yeah, but then I comma sigma I in N is a subset of E. So oh yeah, this is another. Yeah, so what I'm claiming is if this all of these are non-zero, oh sorry, if the sum is if this product is non-zero, then I comma sigma I in N must be a subset of E. Why? Because okay, when can this product be non-zero? If all of these elements are non-zero, right?
Yes, and there is a mapping from I to the sigma of I. I mean, in the bipartite matching.
Right. Yeah. So since the matrix we are looking at is an adjacency matrix, this being non-zero means mi sigma I. So the I comma sigma at entry is one, which means that I comma sigma I is an edge, right?
Yes.
Yeah. So this is non-zero. This is a subset of E. Since sigma is a permutation, it is also a perfect match. Okay. Why? Because okay, when would this be a perfect matching? If for every uh, okay, so for every element 1 to n on the left hand side, you had a unique element 1 to n on the right hand side, right?
Yes.
And that is true because sigma is a permutation. First of all, its range is 1 to n, and it maps like it maps 1 to n, so it's an 1 on 2 map, right?
Hmm.
Yeah, so that's why it's a perfect matching. So for example, let's say 1 maps to 2, then nothing else would map to 2,
Uh, s- yes, yes. So if one is mapping to two, then no other element can map to two.
right? And furthermore, for every element, there would be some element mapping to it.
Uh, there would be some elements which are mapping to the no, no, it can never happen that more than one elements are mapping to the same
Yeah,
element.
yeah, that is true. What I'm saying is for every element on the right hand side, there would exist an element on the left hand side mapping to it.
Yes, yes, because of one two
Yeah,
thing.
right. Yes, that's because of one, two thing, right? So because of that reason, this is a perfect matching because for everything in the left hand side maps to something on the right hand side, but no two things on the left hand side map to the same thing, right?
Yes,
Yeah, so this is a perfect matching. Is this fine?
yes, yes,
Yeah, and this proves the claim, right?
yes, yes.
Yeah. So basically, all you have to do is compute the determinant, look at which, find a sigma for which this is non-zero. That is a perfect matching.
Yes.
Yeah. So now using claims one and two, can you tell me which option is true? These two we have eliminated.
Mhm.
Yeah.
So since perfect matching is not there,
Right.
so it shows that both the determinants and the permanents are zero. This should be true.
Yes.
This should be
Yeah.
true clearly. And but it cannot happen that permanent is zero, but determinant may not be zero.
Yeah.
So therefore, yeah,
Yeah. So only A is true.
yeah.
And okay, so one more thing before we move to the next problem. Look at the difference between the two claims. So the first claim gives a very clear characterization of perfect matchings, right? Permanent equals to the number of perfect matchings. But
Mhm.
this claim is much weaker, right?
Mhm. Yes.
In particular, all it says is the determinant can be anything. It need not be equal to the number of perfect matchings. Just that
Mhm.
if it is non-zero, then there is a perfect matching.
Yes.
In fact, even the converse is not true.
Yes. Yes.
Yeah, so and it's very easy to see that the converse is not true. So yeah, let me just show you that and then we can move to the next one.
So I'm just asking this thing out of
Yeah,
curiosity that since we have some relationship in between the eigenvalues and the determinant thing,
right.
so can we extend whatever conclusion we are drawing here somewhat related to the eigenvalues?
I mean, yes, you can say that at least one eigenvalue should be non-zero.
Okay.
Okay. So, or rather like this, if at least one eigenvalue is non-zero, then G has a perfect matching.
Okay.
Yeah. And converse of claim 2 is not true. Okay, so let G be. So, do you know what K2 comma 2 is? Or should I define it?
So it is a complete graph wherein every vertex, I mean, is 2 comma 2 means
Right.
2.
It's this. So, there are
Yes.
two vertices on both sides. Every
Yes.
vertex on the left hand side maps to every vertex on the right hand side and vice versa.
Yes.
Yeah. So, okay, what's the adjacency matrix of this? It is 1, 1, 1, 1, right?
Yes.
Yeah. Now G has two perfect matches, but determinant of M is zero.
Is 0.
Yeah.
Yes. Right.
And in fact, uh, you can extend this to K n comma n for any n. Yeah. So if you took the adjacency matrix, computed its determinant, and obtain a non-zero value, then you can say that there is a perfect matching. But if you got a zero value, you cannot say that there is no perfect matching.
Yes.
Yeah. So is this fine?
Yes. Yes.
Yeah. So let's look at the next problem. So the next problem is, uh, Let us consider the following family H of pairwise independent hash functions from 0, 1 to the n to 0, 1 to the m. H equals to h of AB of x equals to ax plus b mod 2, where A is an m cross n matrix and B is a vector in 0, 1 to the m. Suppose H is chosen uniformly at random from script H. Given three distinct vectors x, y, and z, and three vectors r, s, and t, what can we say about the three events? Event number one, hx equals r. Event number two, hy equals s. Event number three, hz equals t. All three are independent. Any two of the three events are independent, but not all three considered together. Any two of the three events are any two of the three events are not independent, and the three events are mutually exclusive. So which of these is true?
So actually, this problem statement is not that clear that
Okay, so what the problem statement is saying is the following. We have this family of pairwise independent hash functions. Okay, so it's a set. From this set, we are picking one element at random,
mhm,
and that element is going to be a function, right?
mhm.
Because this is a set of functions, right?
Yes.
So an element picked right uniformly at random from the set is going to be a function. Let me call that function h. Now we have three events: hx equals r, hy equals s, and hz equals t. And the
Okay.
question is, are these three independent or not?
Okay. So like here, say the product of AX would be, so what will be the dimension of this? The meaning of AX is A is a matrix, and then
X
this
is a
will
vector.
X is a vector of M is M. So I mean, what will be the dimension of AX then?
Okay, so
Uh,
the dimension of A is n cross n. The dimension of X is n cross 1.
uh,
So the dimension of AX will be m cross 1. M
M
rows
cross.
n cross. Yeah.
It will return a vector, isn't it?
Yeah. Vector in 0, 1 to the m.
And then we are adding the vector AX with B, and then we are taking XOR. I mean, we are taking the XOR of the outcome of AX and B. Is it?
Okay. It would, yeah. XOR if like by this multiplication, so like in this multiplication, you would have some additions, right?
Yes, but then this AX will result into a vector of the dimension M cross 1 only.
Yeah, yeah. Okay, so A is uh, so A is m cross n,
Hmm.
and uh, X is m sorry n cross 1. So AX equals m cross 1. I shouldn't write equals.
Okay.
Yeah.
And so the dimension of B is also N cross 1. So then how can we add AX with B then?
Oh, entry wise. So you can add two vectors, right?
Yes, yes.
Yeah.
Okay,
So
okay.
addition of vectors and multiplication of matrices with vectors is well defined, right?
Yes, yes.
Now one way to do it is this, as you said, you want if you want to XOR AX and B, you should be careful that while multiplying AX, so what would you do? First row multiplied with X, right? Second row multiplied with X and so on.
Hmm.
Yeah, so in those, instead of additions, you also should have done XOR.
Hmm. Hmm.
Yeah, so basically, everything is mod 2. So every multiplication is an AND, every sum is an XOR.
Yes.
Yeah, that's one way to look at it. Another way is like do your normal arithmetic. At the very end, go mod 2.
Hmm.
Yeah, so these are two ways of looking at it.
So now we have been given three distinct vectors, RS and then T.
Yeah. No, no,
Yeah.
R and T are not distinct. X, Y, Z are distinct.
Three distinct vectors, X, Y, and G, right? And then three vectors, RS and then T.
Right.
Okay.
And over here, H is random, right?
Yes.
Yeah, so okay, so this is the family of pairwise independent hash functions, right? That is given over here.
And so, what's the meaning of the pairwise independent thing? This thing.
Okay, so okay, let me define it. Right? Okay, so yeah, so uh, H is a okay. So first of all, there is nothing like pairwise independent function. You only have a family of pairwise independent functions. Okay, so H is always a collection of functions, and you pick something random at random from it. Okay,
Hmm.
okay, so let me write this over here.
And which one is smaller here, N or M?
It doesn't matter.
But then we are squeezing this x by applying some hash function into a value y. So y has to be smaller in comparison to x. So therefore, the value of
Wait,
m should be lesser
why?
than x.
Why does it have to be smaller?
Because we are
It,
applying the hash function over the value of x.
oh,
So
okay. Okay, in complexity theory, hash function is not necessarily something that compresses.
okay, okay.
Yeah. So, okay, if the word hash is bothering you, you can ignore it. So, in complexity theory, m need not be smaller than n, but yes, in most applications that you would encounter, that would be true. But even in complexity theory.
Okay, so it could be anything.
Yes, okay. So, if it bothers you, let me just remove this. Yeah, so H is a family of pairwise independent functions if number one, probability H picked uniformly at random from H of x equals y is 1 over 2 to the n. That is, if I were to pick a random function from H, it would map the strings uniformly at random in the codomain.
Hmm.
So essentially, H is a family of random functions. Okay, so you want to basically model a family of random functions using a smaller family.
Okay.
Yeah, so the first property says is that H sort of behaves as a random function. In that, if you pick an element uniformly at random from H and apply it to X, Y could be anything from 0, 1 to the n with equal probability.
Hmm.
So it's basically something like this. You pick an X and it's something arbitrary from 0, 1 to the n.
Hmm.
Yeah. And what the second condition says is the following. If x and x prime are distinct,
Hmm.
then these two events are independent.
Hmm.
Why? Because there is an and over here, and this is just the product of these two, right?
Yes, yes,
Yeah.
right.
So what this is saying is the following. You have events of these type. When you have events of this type, and you have just one event, it's completely random. When you have two events, they are independent.
Yes.
Yeah. The question is, we have a family of pairwise independent hash functions, and we have instead of two events, we have three events. Okay.
Uh-huh.
And the question is, are the three independent? Are they not independent? If they are not independent, are only two of them independent? And so on, right?
Okay.
Yeah.
So
So,
I will deny this first option that all the three events are independent, because if we compute the joint probability of, say, this x, y, and then g,
hmm,
since x and y are independent and y and g are independent, so
right.
therefore the joint probability of x, y, z is equal to the probability of
Oh,
y
yeah.
given x and multiplied by the probability of g given x and y.
Okay.
And since the probability of y given x is same as the probability of y, it does not depend on x here.
Hmm,
So the formula comes out to be the probability of x multiplied by the probability of y and multiplied by the probability of g given x and y.
okay.
And yeah, but then since y and g are independent of each other, so therefore the last term will become the probability of g given x.
Okay.
Uh, but is this necessary in the pairwise independence? So this z can also be independent of the x then?
Yeah, that
Uh,
is true.
that
That
is
is in the
true.
definition, right?
Yeah, so in that case, the P of x, y, g will be the product of x, the probability of x multiplied by the probability of y multiplied by the probability of g. So in that case, the first option is seems to be correct then.
Okay.
All
Yeah.
the
So there was one mistake in your analysis. So you were saying that probability of z given x comma y equals probability of z given x, right?
so I said that probability of z given x comma y, if z is independent of
Yeah. Yeah. So okay. So
probability of z
okay.
given x
So
comma y would be either equals to the probability of z given x or the probability of z given y. Depends that whether z
yeah.
is
Yeah.
independent or
Yeah,
not.
so that claim is false. So even if x, y, and z are pairwise independent, that is, even if z were independent of x, and if even if z were independent of y, probability of z given y comma x is not the same as probability of z given x or z given y. It need not be the same.
Yes, yes,
Yeah, and
yes.
I think, yeah, I mean, examples should be easy to construct. But yeah, for example, yeah, okay. So let's say you toss a coin.
Uh-huh.
You toss two coins.
Uh,
Uh, X is 1 if and only if the first coin is head. Y is 1 if and only if the second coin is head. And Z is X, X or Y.
Z is
Okay. Okay, so let me write it. X equals 1 if and only if first coin is heads. That is if and only if exactly one of them is head.
okay, okay. Yes,
Yeah.
yes.
So now Z and X are independent. Why? Because, okay, if X were 1, what is the probability of Z being 0? It's still half.
Hmm.
Yeah, and similarly, Z and Y are also independent. So, okay, let me quickly prove this first thing. So, what is probability of Z equals 0? Yeah, because why is this? Because in the, if you look at the truth table of XOR, exactly two entries are zero, two entries are one.
Hmm.
Yeah, so this is half, right? So now what is probability of Z equals to zero given X equals to zero? This is probability uh, Y equals to zero and hold on. So this is the same as probability Y equals zero. Okay, so X is you are given that X is zero, and when can Z be zero? Y is also zero, right? Okay, so what's the truth table of XOR? So suppose I've already told you that X is zero, then when can Z be zero?
So if x is 0, then yeah, so it is happening only in the first row.
Right. So X is zero, Z is zero, means Y has to be zero, right?
Yes.
Similarly, when X and Y are both zero, Z is zero.
Mhm.
So basically, these two events, Z equals zero given X equals zero and Y equals to zero, they are equivalent, right?
Yes, yes,
Yeah.
yes.
And this is half. Similarly, probability Y must be one.
But then this value of xy in the z could be should be 0 here if both are same in this table. Last entry should be in
Oh
the
yeah,
last
yeah.
entry.
Sorry. Yeah, I wrote the table for or.
Yes.
Yeah. So we have these four things, right? So
Yes.
the probability of Z being zero or one does not depend on what X is, right?
Right.
So Z and X are independent, and similarly, you can say that Z and Y are independent. It's exactly the same argument, right?
Yes.
But probability Z equals to zero given X equals to zero, Y equals to zero is not half. It is one.
Mhm.
Yeah. And okay, so what you were saying is that this should be equal to this, right? So you were saying that if Z and Y are independent, these two should be the same, right?
Yes.
Yeah, but this is not the case.
Yes. Yes.
Yeah. And in fact, yeah, that's one of the crucial things that this question asks. So what this question is asking is, we know that every two events are going to be independent.
Mhm.
Are all the three independent as well? That is what this question is asking.
Mhm.
Yeah. So, okay, we don't know whether A is true or not. We can't say anything about B yet, but we can definitely rule out C, right? Sorry, we can definitely rule out C
Any
because
two of the three events are also not independent. So yes, we can rule it out. Yeah.
that's the very definition of independent functions, right?
Yes.
And all three events are mutually exclusive. That we can also rule out because independence does not imply mutual exclusiveness. In fact, they are the exact opposite of each other.
Mhm. Mhm.
Yeah, so we can rule out these two.
Now, any of the two of the three events are independent, but not all three considered together.
Yeah, so okay, this part is true, right? The first part.
Yes.
So all we need to find out is can the three events be independent or not? Okay.
There was some issue with your video. Yeah, can you please repeat the statement?
Yeah, so what I'm saying is the question boils down to finding out if the three events can be independent.
Okay. Yes.
Yeah. Okay, so let me tell you the answer is A. Sorry, the answer is B. Yeah. So all three events are not independent. And what I'll do is I'll show that there exists X, Y, Z, R, S, T, such that the events are not independent. Okay.
Mm-hmm.
Okay. So, any, okay. And what about any three events? So, suppose, okay, so you have Hx equals Rn, Rhy equals S, Hz equals T. So this means Ax plus B equals R, Ay plus B equals S, and Az plus T, Az plus B equals T, but I'm not writing it. And this implies that A of X minus Y equals R minus S. Okay,
Yes.
so now let X, okay, let Z be X minus Y, and let uh, T be R minus S. Okay, then the above says that AZ, oh wait, no. Let me modify T. Yeah, now I can see it. Okay, so the above says that AZ equals T minus B, right?
Mm-hmm.
Yeah, so if we fix X, Y, and Z like this is what we get. Now, probability of HZ equals T given HX equals R and HY equals T. So what is this? This is 1, right? So if my, sorry, HY equals this.
Mm-hmm.
So if my X, Y, and Z were defined as, if we have defined them above, then this probability would be 1, right?
Mm-hmm.
Yeah, so is this claim fine?
Yes. Yes.
Yeah.
Yes.
And for independence, we need this probability.
is equal to Z
Yeah.
is equal to T given Hx is equal to R and then multiplied by the probability of Hz is equal to T given Hy is equal to 5. Hy is
Yeah.
equal to S.
Right. So I can like just skip that step and write this. Right.
Yes.
Yeah. But what is this? This is 1 over 2 to the n. Hmm. Yeah. Because each and every independent event has so each and every individual event has probability 1 over 2 to the n. Right.
Yes.
Yeah.
Yes.
So there exists X, Y, Z, RSP such that these three events are not independent. Right.
So they are not independent under this framework that we are defining the hash function like ax plus b.
Right.
So, so had this been a different, I mean, mapping, then we could have, I mean, find
Yeah.
three independent. Yeah.
Yeah. So okay. So here H is a family of pairwise independent hash functions. Right.
Mhm.
So you can also call pairwise independent hash functions two-wise independent. And you can analogously define k-wise independent for any k. So you can
Oh,
have three-wise independent hash functions, four-wise independent hash functions, and so on.
okay.
And for k-wise independent hash functions, you have similar conditions. So this is as it is. And over here, instead of just two events, you have k events or up to k events.
Okay. Okay.
Yeah. So this holds true for two events, three events, four events, up to k events.
Okay. Okay. Yeah.
Yeah. And like the constructions are similar. So this is a degree one construction. So, okay, let me say that M and N are both one. Okay. So then this would just be AX plus B.
Mhm.
So one way to define three-wise independent hash functions would be AX square plus BX plus C mod 2.
Okay. Okay.
And one way to define K-wise independent hash functions would be AX to the K plus BX to the K minus 1, so on, plus C equals mod 2. So
Mhm.
basically take a random polynomial of degree K.
Mhm.
Yeah. So this question fine?
Yes. Yes. Yes.
Yeah. And so he has started counting complexity, right, from this week.
Yes, the counting complexity had started. This sharpie had started.
Right, yeah. So in counting complexity, like pairwise independent hash functions would be used crucially at one place.
Okay, so
Yeah.
because in the week 9 only the introduction of the this sharpie was given,
Okay,
and,
yeah.
and the details probably were there in the week 10.
Okay, yeah.
That Toda theorem, etc.
Yeah.
Is
So
there?
yeah, so it will come as a part of Kudas, as a part of the proof of Kudas theorem.
Okay, okay.
Yeah. Then let's look at this year's week 9 practice assignment. The first problem is from the below choices, choose the most accurate statement of Mulmule Vazirani algorithm for outputting a perfect matching in parallel. It always outputs a perfect matching. It does not necessarily output a perfect matching, even if there is a unique minimum weight perfect matching. If there is a unique minimum weight perfect matching, it outputs the perfect matching. And if there are multiple minimum weight perfect matching, it outputs a perfect matching. So which of these is true?
So this Vajirani theorem does this indicate that if we find the subsets of a set, then there would definitely be a set having the least value. So what this theorem, Vajirani theorem is, can you please uh,
Wait, which
find
theorem?
the statement of this?
Oh, so okay, there is
This
no
Vajirani.
theorem, there is an algorithm over here.
Oh, I see. So yeah. So
Basically, that algorithm that was covered in class to find perfect matches.
Okay, so I have no idea of this MVV algorithm. Now
Yes,
I'm.
yes, yeah, yeah, yeah. So, okay, so what that algorithm does is the following. It tries to find a minimum weight perfect matching. So for every perfect matching, it assigns a weight in some way
Okay.
using randomization. And if it finds, if the weight assignment is such that there is a perfect matching with minimum weight, then it outputs that perfect matching. So the only randomness in the algorithm is in assigning the weight, is in the weight assignment. And if the weight assignment succeeds in the sense that there is a minimum weight perfect matching, then the algorithm succeeds in outputting a matching. So C is true. Yeah. So if you go back and look at the algorithm, what you will see is that the only point of failure in the algorithm is a failure to have a unique minimum weight perfect matching. So if let's say two or three perfect matchings have the same weight and they are minimum, then the algorithm might fail. But if there is a unique minimum weight perfect matching, the algorithm would always succeed. Yeah.
Okay. Okay.
Yeah. So the next problem is which of the below statements would imply that P equals NP? Select all that apply. There is a deterministic polynomial time algorithm to count the number of satisfying assignments of a Boolean formula. There is a deterministic polynomial time algorithm to count the number of proper three colorings of a graph. There is a deterministic polynomial time algorithm to count the number of spanning trees of a graph. And there is a deterministic polynomial time algorithm to count the number of directed ST paths where S and T are specified vertices in a directed acyclic graph. So which
Uh,
of these four would imply P equals NP?
so I think that A and B, first two options are correct
Yeah,
because for the C, we already have a polynomial time algorithm to count the number of the spanning trees.
right, yeah,
And probably same is true for the last one also. So the first two are correct. So
yeah. Okay, so like why? Okay, why is one correct?
one is correct because if we can find a deterministic polynomial time algorithm to count the number of the satisfying
Hmm,
assignment, so it shows that because the counting is seems to be more difficult than actually getting the solution. Because if I can count the solutions, then it shows that more or less I have solved the problem. And
okay,
in fact in the lecture also, I mean it was mentioned that the sharp of P is even tougher than NP. So
right. Okay, so
so
what I'm asking is why is that even tougher than NP?
okay, so fine. So if I can count the solution, then indirectly I have solved the problem.
Okay, so yeah,
And
which problem have you solved?
moreover,
The decision version or the search version?
yes, so yes. So this is a search version that I'm counting the all the solutions of the problem using a deterministic machine.
Right.
So yes, if I can count the solutions, so yes, this is a decision variant, but then basically I am
Okay, okay. First
counting
of
that
all,
how many times did I get yes.
this is neither a decision version nor a search version. The problem is a counting version. Okay. What I'm
Yes.
asking is, if you solve the counting version, which version have you solved? The decision version or the search version?
Okay, so if I can solve this version of the problem, then I have already solved the decision variant of the problem because then I can
Yes.
always count that okay these many times I got the value as yes.
Right. Yeah. So basically, there are three versions of the problem: decision, counting, search.
Yes.
Counting version, solving the counting version implies that you have solved the decision version. Why? Because okay, so uh, given phi or given a Boolean formula phi, uh, Agreed. Yeah. So this is true, right? So what we can do is given a Boolean formula phi in a polynomial time, count how many satisfying assignment it has. So if five are in set, it would have at least one satisfying assignment, right? So m would be at least one.
Yeah.
Similarly, if five are not in set, m has to be zero.
Yes.
Yeah, so by solving the counting version, you can directly solve the decision version.
Yes. Yes.
Yeah. And if you recall from the first or the second week, for NP-complete problems, search and decision are equivalent, right?
Yes, rather optimization and the decision variants are one and the same thing. I mean,
Right.
if we solve the optimized one, then we would also solve decision.
Yeah. So, and reverse is also true, right? If you solve the decision version, you still solve the optimization version.
Yes, yes.
Okay, so that was covered in, I think, the first or second week.
Yes, yes.
Yeah. So at least for NP-complete problems, if you solve the counting version, you have solved the decision version and therefore also the search version. So for NP-complete problems, the sort of the hardest is the counting version.
Yes.
Yeah. Okay, so the next problem is the MVB algorithm shows that the problem of outputting a perfect matching of a given bipartite graph is in which of the following complexity classes: RP, NC, AC, RNC, or P slash pool.
So I've not gone through this MVV thing.
Yeah,
Just now you told about this MVV.
yeah. So it's RNC.
Okay, so what this
Yeah,
R here in this NC? I know that this NC thing wherein we
right.
have
Yeah,
multiple fannings at the end,
right.
and what this R here stands for?
Okay, so R stands for that. Okay, so in an NC circuit, you have two inputs, X and a random string.
Okay,
Yeah, so in an RNC circuit, you would have two inputs. So an RNC circuit is the same as an NC circuit, except that it has this extra input R, and
okay,
for most of the R's, it should accept. If the string is in the language, for most of the R's, it should accept. So it's like P and RP, but for NC.
okay, okay.
Yeah. So the next problem is given out of the given Boolean formulas, which one is the yes instance of USAT? All the below formulas are to be considered as formulas over two Boolean variables, x1 and x2. Select all the options that are correct. X1 and x2, x1 or x2, x1 complement, and x1 or x2, and x1 complement or x2, and x1 or x2 complement. So which of these are yes instances of USAT? We can go over this option by option. So what about the
Okay,
first option?
so the first option is correct. I mean, first option is first option is not correct because we can have two different assignments here. Uh, so yes, because this is USAT. So no. We can
Yeah,
have
yeah,
only
yeah.
one assignment. X1
Yeah,
has to be true, X2 has to be true. So this is
right.
true. This is true.
Yes.
And or so this is not true. The
Yeah, because
complement of
three
X1
assignments,
is
right?
not true because X2 is not here.
Yes.
And the last one, X1 is not true because X2 is not here. So this
No,
is
X2
not
is here, right?
uh, in the complement of X1. Where is X2?
But this one?
So I mean this is the last option. Below this there is only one X1, the complement of X1 only.
Oh, sorry. Yeah, yeah. Yes, yeah,
So yeah. So now the last one is correct. Yeah.
yeah. Yeah, so the last one is, I think we already saw this, but let me just do it again. Oh, wait, okay. Okay, I'm not sure that okay, maybe even this is not correct. Let me just work it out first. Yeah, so this is the equivalent to I can take x2 common from the first two, so it's x2 and x1 or x2 complement, and this means that okay, it's x2 and x1. Yeah, so this is just x1 and x2.
Same as the first option.
Yeah, so this is also true. Yes, A and D are true, B and C are not. Yeah. So then, let's look at the last problem. So which of the following options captures the message of Valiant Vazirani theorem most accurately? USAT is easy. USAT is not easy but easier than SAT. USAT is likely to be roughly as hard as SAT, and USAT is much harder than SAT.
So uh, USAT is not easy, but
Yes.
uh, clearly this is easier than SAT because we have don't care conditions.
Oh, in fact, it's the other way around. So a SAT randomly reduces to 3 SAT. So there is a randomized polynomial time algorithm says that if you input a yes instead of SAT, it would with high probability output a yes instance of USAT, and if you input a no instance of SAT, it would input a no instance of USAT.
Okay.
Yeah, so SAT random. Okay, so it's this SAT. Yeah, so either C is true or D is true, but we don't expect USAT to be much harder than SAT. We expect
Yeah.
them to be like roughly of the same difficulty.
Yes.
Yeah.
Yes.
Okay, so now like we have only like 7 or so minutes. So uh, before like starting with week each assignment, if you have any questions or if you have any preferences for like which questions I should solve in week 8, then you can tell me now.
In week 8 or in week 8 or in week 10?
No, no. So okay, this we will solve this year's week 8 assignment, right? So week eight's deadline has passed.
Okay. Yes.
Yeah, yeah,
Yes. So in the week 8, which topics were covered? So in week 8, it's a parity thing. Yeah.
yeah.
So and
AC
then
zero. Yeah, parity not in AC zero.
yes. So if you can focus on this polynomial identity testing thing because this was not clear at all. Or
Okay. So
someone, I mean,
The
this.
first question, if you can explain.
okay, yeah. Okay, so let me do this. Let me first explain the first question and then talk about PIT.
Okay.
So the first problem is someone had already written the answer. It's
Oh,
P.
I did not understand your question. Probably you asked that since 7 minutes are remaining. So, I mean, out of the remaining
Yeah.
questions, which I thought that you are asking for the topic to be discussed in the next problem solving session. So,
Okay, okay, okay. Okay, so okay, if you want me to explain PIT to you in the next session, I can do that.
yes, so if you can give a brief overview of that, that identity testing and this RNC thing, so that will be fine.
Okay, yeah. Okay, the RNC algorithm is like a bit. So the RNC algorithm for perfect matching is a little involved.
Okay, okay,
Yeah,
okay.
but okay, I can tell you about the polymer identity testing part.
Yes, yes, that would be great.
That would be very simple. Yeah. Yeah. So the first question was which of the following polynomials over reals represents the or already said the answer is D. So yeah, here's how you can do it. Uh, so one of the De Morgan's laws says this: x1 or x2 or up to xn is the same as the complement of yeah. So we'll use this law. Now, okay, let me write. Okay, so now we know that uh, not x1 is the same as 1 minus x1. Not x2 is the same as 1 minus, and is just a product, right? So this thing is the same as this product, but there is still this complement outside. The complement is just a not of this thing, right? So it's 1 minus, yeah, because not x equals 1 minus x, and x and y equals xy. Yeah, so this is one way to prove that or is the same as this polynomial. So is this fine?
Yes.
Yeah. When is this polynomial non-zero? It is only non-zero when this is zero, right? And this would be zero whenever any one of this is one. So this polynomial is non-zero if and only if at least one of the xi is one, which is exactly the OR function, right?
Yes.
Yeah. So this is another way of showing that say this is OR.
Right.
So like, were there
So
any other questions that you want me to solve?
I have a query that can you suggest some course homepage or some other book wherein a concise content is given and with lots of these solved problems apart from the Sanjeev Arora book which is slightly difficult
Okay.
to understand.
Yeah. The problem is,
You are on mute. I could not hear you.
okay, so I was on mute in my iPad, not on my computer. So yeah, uh, the problem is that there isn't any resource with solved problems.
Okay, okay.
Yeah. And okay, so I generally follow the Sanjay Arora book, so I don't know of any other online like set of lecture notes or anything.
Okay, okay.
Yeah. Yeah, but I think uh, okay, so if you look at some problems in Sanjeev Arora's book, Arora Bharat's book, and you search for their answers on the internet, you will find them.
Yes, actually, I find the solved problems, but then these problems are dispersed at many places. So I could not
Yeah,
find you.
yeah, that is the issue. In fact, I the reason that that book does not have a solution manual, and that is the following. So the authors of the book intended the problems to be something that you can ask in exams and give for assignments.
Oh, I see.
Yeah. So even the complexity theory course I did, most of its exams and assignments were from that book.
Okay, okay,
Yeah.
okay. Yes. But I think that even these homeworks are also, pretty good. But still, for the practice purpose, if we can, yeah, get something.
Okay. So I can do one thing. I was the TA for this course last year as well. What I can do is I can give you link to those slides.
Okay. Uh,
Yeah.
you were on mute. Yeah.
Yeah. So okay. So what I was saying is in those slides, you can first look at the question, try to solve it on your own, and then look at the solution. Okay. That
Yes.
should help with practice. Okay. So let me find those slides. I think it's a Google folder. I can give you a link to that folder.
Yeah.
Mm, Yes, sorry, I accidentally logged out. Yeah, so this is the link.
Yes. Yeah.
Yeah, yeah, so
Yes, and it is opening. Yeah. Fine.
yeah, yeah. Okay. Yeah, so if there are no other questions, we can meet next time.
Yeah. Thank you. Thank you so
Yeah,
very much. Bye, everyone. Good night.
bye.
But
Thank you.
Bye.